Now after we have compiled it, so we need to upload our program to the board. So we can go to our programmer. You see now it has detected our board. So we did last time, and we have the same file. So we can just press start here, and I can see my board is flashing. So let's look at the board, and I'll show you how I have connected, and the same way you should connect at the lab too, to measuring the delay. So let's look at the board. Now we are here at the board. So this is kind of setup I have. I have connected the board to the power supply, and this to the computer that has a Quartus program. So this is the output signals that I was talking about, the GPI for the output and input signal. So our input X0 is this yellow one, and our input is the blue. So we have two probes here. So this probe is for the yellow color, which is the X0 axon, and this is for the output, which is for the majority detector. And then we have a common ground, which is this pin. So the first two pins are for the output, and the pin number 6 you can reference to the manual and see that this one is the ground. So I have connect both to the common ground, as you can see. Now let's look at the oscilloscope. So first of all, we need to trigger the majority detector. As you can see here, majority detector is not on. Although if I press the first X0 is not on, but you can see the X0 is toggling between this value. So you can see that we have 2 volt per division. So we need to change it, for example, to 1 volt per division. And scale it here. So when I change, you can see I can scale from up and down with this. So you can go to 1 volt, and then we need to find a 0 point, because now we take it to the 0 here. So we can see that we have 1 volt, 2, 3, 3.3, the same as the manual shows 3.3. Another thing you must remember that this push button is active on when you don't press it. So if I press it, it's going to be 0. So if I press it, it's 0. And then we need to take the output majority detector to scale it to 0 too, but we need to change it to 1 volt as well per division. So and then we move it to for 0 point here. So but now you see the majority detector is not, because our majority detector is LED 4, which is this one is not on. So we need to activate it. So we can take all WV, for example, all the WV, so which are CNEPAs on. So we can see when we take the first W0, we have counter is counting 1 because this is on. So our drain right will be on since axon and CNEPAs are on. So we have 1. So the count is 1. Now, in order to activate a majority detector, we can flip the second switch here to on, so X2 is on. So then we have, because we must get counter to be 2. So because that way we can have a majority detector. So if we flip count this one to 2, you can see our majority detector is on. When I turn it off, it's 0 and on. So now we can use our button now to turn on and off. So now we want to measure delay from this X0. So when I press this button to where the output of majority detector, the light comes on. You can see it's reflecting on the screen here. So let us try to capture that delay. There's some delay there, we need to capture it. So one way to do it is to go to the trigger menu here. So you can go to menu. So you have a trigger menu here. And then we need to choose our source. So our yellow source is, as we said, is the input. So that one we want to trigger on this one at the rising edge. So we can choose here. So now we want to capture it at the rising edge, and the level we want to capture is half of it. So it's going to be 3.3 volt divided by 2, so it's 1.65 volt. So we need to change this one to 1.65 volt. Roughly there. So you can see it's half of it. You can see it's half of 3.3. Now after we have set that, you can just turn off there. Turn off the menu, and then we can go to single shot, and then we can trigger it. So if we press now, it will capture when it at the rising edge. Yes, now it has captured. So there is some delay here. We need to zoom in and look at that delay. So here, this button here is for scale. So we need to zoom in. Oh, it disappeared. Okay, let's just zoom to 2 nanoseconds. So I think this delay roughly is very low, so it's 2 nanoseconds. So we need to scale to 2 nanoseconds, and then we can go back to single mode, and then we can trigger it again. Then we press the button again, the push button. Yes, now you can see that. Let me turn off the cursor first of all. So we can move it to the middle of from there, and then turn on the cursor. So you have a cursor menu here. We can turn it on. Now at the cursor menu, we need to change to find the 1.65 volt that we have set on the trigger menu. So we can take the yellow one to be A. So if you hold your cursor in, you can choose the source. So we keep it to source 1, which is X0. So we can keep it there, and then change it to try to find it 1.65. So we are looking at here at A, 1.65 volt. that we have set it. Roughly there. And then we need to change the source again. So now we don't touch again this one because we just set it up where we want it. Now we can go to B, but now we need to change the closure. Hold it in and select source B. So you can select with A again here, but so now we have changed the source to source B. So that is the two signal, that is our majority detector. Now when we turn this button here for cursor B, you can see it's marked B. Let me turn it off. It's marked B. So if we change it and try to find it again, so we are in B here, try to find 1.65 volt. Roughly there. So we can see that here is our delay. Delta T is this one. So you can see it take A, which one is 1.65, and B is 1.65 volt. This is the delay between here, which is about 1.722 nanosecond. So let's just try to find this 1.72 nanosecond, roughly about that one on the quartus. So this is how you're gonna do it, and you're measuring your delay and how you set up your scope to measure this kind of delays. So let's go back and look at our quartus program. So we can see even here our majority detector is on and our count is on. So let's go back at our quartus program and look at it. Now we're here at the quartus, so let's launch the time analyzer. And now we're going back to custom report, start, path. So our input, as we did the previous, is X0. And our output is debug majority detector and debug X0. Okay. Report path. Now, so the first one we have, so as we show on that picture, we had X is roughly about 1.72 nanoseconds. So we need to find it here. So remember here I'm sitting at the lab, and we have you can see here, this is the board. It estimates that the board is slow with input of 1.2 millivolt at 85 centigrade. But here I'm sitting is roughly, I will say 25 degrees, less than that even. So we need to go to, I think these two are most common scenarios. So let's generate all the corner cases and just look at this one. So if we take a look at this one, this will give us roughly about 2.9 nanoseconds. And this one will give us roughly 1.8 nanoseconds. And this one will give us roughly 1.68. So I think this one is the most common, more reasonable answer. So let's go at the whiteboard and see how was our expectation like. So now if you go to our board, so we can explain that for example here So we had our x0 like this. We had our debug signal like this. So this one was the delay time dt that we have measured. Here was at the top, here is 3.3 volt, and we have measured here half of it for both, which was 1.65 volt, and then that was time in nanoseconds. So this was our initial expectation that we look, but we remember that this one is for slow, and then it was 85 centigrades. But what we have measured, if I take a look at my scope now, we have measured dt here is equal to 1.72 nanosecond. So this it look more likely this one for fast and at the 0 centigrade. That this is estimation. They are looking at when it is fast. So they estimate that the model is fast at 0 centigrade, and then we have so our x0, so db x0 is equal to 6.054, and db merge detect 3070. So both of them are nanoseconds. So if we do our mathematics here, dt is roughly 1.684 nanosecond, and we measured this one, so I can roughly say it. So this is more like scenario. So we need to put all the traces that are in here, and plus the delays that are on the wires to the scope. So we can see roughly this is about how you're gonna measuring the delay. So now we have looked at all the tutorials from basically from how you design your model, how you simulate it in the test bench file, how you deploy it on the board, and how you estimate the time delay, and how you measure it onto the scope too. So, and then we're gonna look at the next topics in the next videos.